In this video, we're going to look at what sound is physically. So we'll look at that in terms of pressure fluctuations within a medium. Then we'll move on to look at some of the impacts of sound or noise on humans and how we react to that sound or noise. One way to think of sound is that it's the result of the movement of a mechanical device or system that displaces a surrounding medium. That medium may be a solid, a liquid, or a gas, and the displacement of the medium produces a local compression followed by a local rarefaction. Let's look at something with which you may be familiar, a tuning fork. When you strike a tuning fork, the prongs vibrate. That movement of a prong displaces a medium. In this case, that's the surrounding air around the tuning fork. When those pressure fluctuations reach our ears, we perceive these as sound. In the case of a tuning fork, the dominant frequency of the sound would be due to the vibration of the fundamental mode of a prong of the fork. In the animation, we see the prong of the tuning fork vibrating backwards and forwards. As it vibrates, it displaces the medium, and we get these waves propagating out away from the tuning fork. Let's look at another type of displacement of a medium that generates a sound. Consider an oscillating diaphragm. Thanks to Dr. Dan Russell for this animation. The diaphragm is able to move backwards and forwards, and as it does, it displaces this medium. And we're going to identify small parts of this medium by these dots. So each dot represents a little bit of a parcel of this medium. So what we see is the medium moving backwards and forwards. Let's zoom in and look at a small parcel of this gas, or one of these dots. And what we see is that dot is just moving backwards and forwards. So the medium itself is not moving away to the left or the right, but these little packets of gas are moving as the sound wave passes through them. So we get a sequence where the medium is compressed and then expanded, and these compressions and expansions travel at some finite speed out through the medium. Let's now take a snapshot of that medium. At the top here, we've got that snapshot. And plotted below is how the pressure within the medium varies with distance along this pipe, along which the sound wave is propagating. So here we have pressure plotted vertically and distance plotted horizontally. We see that there are regions where the particles are located close together and regions where they're located further apart. In the regions where they're located close together, we get high pressures, and the regions where they're located further apart, we get low pressures. So that's our compression and our rarefaction. So the wave is made up of a series of these compressions followed by rarefaction, followed by compression, followed by rarefaction. And so it's this compression and rarefaction that is the sound wave propagating through the medium. We can formalize this with the definition of sound. So sound is a mechanical disturbance propagating through a medium that's capable of exciting the sensation of hearing. Similarly, we can define noise. Noise is a sound that's unwanted by the recipient. So what we call noise is a subset of what we call sound, and we differentiate that subset by it being undesired by the recipient. Let's now concentrate on that unwanted sound, noise. If we have noise at very high levels, then there's potential that that noise can cause damage. One possibility is that it could cause immediate hearing damage. An example of that would be the noise from a gun or a cannon. You could potentially damage your ears immediately if you were not wearing any hearing protection and you were standing very close to the source of that sound. It's also possible that very high levels of sound could cause structural damage. An example of that would be noise from an explosion that causes pressure fluctuations to propagate through the air and impact on a surface. An example of this would be where you'd see windows blown out as the result of an explosion. Another example of noise at very high levels is the sound produced by an aircraft when it's travelling close to or faster than the speed of sound, a sonic boom. There's a nice video on YouTube by an organisation called avweb.com that I'm going to show here. It gives some good examples of sonic booms generated by aircraft and has a nice explanation of what you see sometimes from aircraft travelling near the speed of sound.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
I think that's a really good description of what you see sometimes when you have an aircraft flying close to the speed of sound and you see a cloud forming. What you're actually seeing is the effects of the shockwave on the air that the aircraft's passing through, rather than visualizing the shockwave directly. Having said that, you can sometimes see shockwaves directly due to how the density changes due to the shockwaves. If we go back to the video and we look at that still photograph of the F-18 aircraft, you can see some distortion in the background due to light being refracted through these density gradients. This is called a shadow graph effect. When you do get sonic booms occurring near residences, there's the potential for them to generate some structural damage. I'm going to show a couple of photographs here, courtesy of Professor Neil Page, that shows structural damage caused by sonic booms at a residence located near where an air show was being held. Here we see a broken window. We can also see the glass shards on the windowsill. And in this photo you can see some plaster that's been dislodged near the ceiling due to this sonic boom. So you can get structural damage from sonic booms, and this is one of the reasons why aircraft usually are not permitted to fly supersonically or close to the speed of sound in places where residences are located. Let's reduce the levels of noise from very high to high. High levels of sound can lead to long-term hearing damage. An example is a worker who's exposed to high levels of noise over a long period of time. The level is not high enough to lead to immediate hearing damage, but the long-term exposure certainly can. As acoustical engineers, one of the things we have to consider is whether the noise exposure of workers could lead to long-term hearing damage. Another example of hearing damage is exposure to very large music, say a rock concert. You've probably heard of musicians who have hearing damage due to exposure to high levels of noise over years. So most musicians will wear some form of hearing protection when they're performing or practicing. There's also the possibility that you could get long-term structural damage due to high noise levels. For example, that could be in the form of structural fatigue caused by movement of parts of the structure due to the pressure fluctuations caused by the noise. Let's keep moving down in level and consider what we might call medium levels of sound. Medium levels of sound are those levels of sound that don't cause hearing damage. However, they may cause annoyance. An example of this might be a late night party at your neighbour's place. They may be playing music loudly and you're trying to sleep. The people at the party don't think there's a noise problem. They're happy with the music. It's a sound they want to listen to. However, to you it's an annoyance. So classifying these medium levels of sound as noise can be a value-dependent assessment of the sound. There's also the possibility that medium levels could cause discomfort. Maybe a pure tone could be very annoying. This can be compounded by health problems and psychological state. In summary, noise at very high levels can cause immediate damage, either to our ears or to structures. High levels of noise may not cause damage immediately, but they may cause damage over a longer period of time. Medium levels of noise can lead to annoyance or discomfort. As acoustical engineers, we may encounter any or all of these at different times.